Welcome to part one of the overview of frameworks. The topics we'll cover in this part of the module will first analyze why hardware has historically improved so much more consistently than software. We'll then talk about some of the key characteristics of frameworks that help to improve software quality and software developer productivity. If you look back over the past 2 or 3 decades, it's amazing the advances we've had in hardware. Hardware seems to get better, faster, and cheaper at a very predictable rate. When I first started computing back in the mid-'80s, I was using a very slow processor on a single core. Nowadays, my smartphone has multi-core and is running at over a gigahertz speeds, which is a tremendous improvement. Likewise, when I first began networking over dial-up links, we had 1200, 2400 baud modems. Nowadays, we have hundreds of megabits to the desktop and even more in the backbone. If you take a look over the next several decades, if the rate of technology improvement in hardware and networks continues at roughly its current pace, we're going to have an amazing number of cores running at high clock speeds and more bandwidth than we'll know what to do with. In a sense, hardware and networks have become high-performance commodities. You might want to take a look at the link below for an article I wrote a number of years ago talking about some of the implications of the commoditization of technology. In contrast, software has a reputation, to some extent deserved, of being buggier, slower, and more expensive over time as compared to hardware, which tends to get better, faster, cheaper. In general, software quality and productivity hasn't improved nearly as rapidly or as predictably as hardware. There's a whole body of literature out there on software runaways, death marches, and software failures. And this is particularly problematic for large-scale, mission-critical, concurrent and network software systems, systems where the right answer delivered too late becomes the wrong answer. And it's almost a cliche nowadays to expect these kinds of software systems are going to be delivered late, over budget, and full of defects. Once again, I wrote an article a number of years ago that talks about some of these issues you might want to take a look at. So why is it that hardware seems to improve so much more consistently than software? Well, there's a number of reasons. Chief among them is that advances in hardware and networks stem largely from the maturation of standardized and reusable interfaces, protocols, and modeling tools. For example, the x86 instruction set that we use in many of our computers has been around for a very long time. The instruction sets haven't changed a whole lot in 30+ years. As a result, the hardware engineers who develop these chips are able to put more transistors on a chip, put more cores on a chip, deepen the pipelines, and are able to improve fabrication quality at a very predictable rate. Likewise, routers and switches for TCP/IP protocols have an amazing ability of being able to put packet forwarding into hardware and packet routing into firmware. And once again, we see tremendous, predictable, regular improvements in terms of reliability, performance, and cost. So what's going on with software? Why has it failed to improve as consistently? I think in general, software has not been as standardized or reusable as hardware and networks. In fact, when many people develop software systems, historically there's been a tendency to take each form factor of the hardware and write stovepipe special purpose software applications, infrastructure, and so on. And even when this software runs on top of the off-the-shelf hardware and standards-based networks, there's still an awful lot of reinvention and rediscovery of the core capabilities. Historically, software developers have had to manually redevelop and rediscover these capabilities, making their solutions much more expensive to develop, to integrate, to validate, and to sustain over the life cycle. One of the consequences is that any time anything changes, because these software systems are built in such a brittle and stovepipe manner, that any small modification in requirements, changes in the hardware, changes in the operating system, programming language, etc., tend to have a big negative impact on overall system quality and sustainability. So what can we do to make things better? Well, one of the techniques that's proven to be very effective is to apply software frameworks. A framework is essentially an integrated set of software components that collaborate to provide a reusable architecture for a family of related applications. As you can see in the diagram on this slide, rather than developing software in stovepipes, where each piece of hardware, each custom form factor has its own software stack, full of all the inherent and accidental complexities that must be rediscovered and reinvented manually each time. Instead, frameworks help to promote systematic reuse by factoring out many of the general purpose and also domain-specific services from the responsibility of the application developers. I wrote an article a number of years ago that you might want to take a look at that talks about some of the dimensions of systematic reuse and how they interact with frameworks. There are a number of characteristics of frameworks that help to differentiate them from other forms of systematic reuse. In the next set of slides, we'll talk about some of those characteristics and provide some examples to help make the points more tangible and concrete. You can also take a look at this article, which was an introduction to a special issue of the Communications of the ACM a number of years ago, which provides an overview of many of the same topics. One of the most important characteristics of a framework is that it embodies something that's known as inversion of control, which is also somewhat humorously referred to as the Hollywood principle, which says, don't call us, we'll call you. John Vlasides wrote an article about the Hollywood principle that you can take a look at this URL. Inversion of control essentially involves having the framework be responsible for detecting the events that occur, the multiplexing those events to various handlers, and then dispatching methods on those handlers to carry out the application or service-specific processing. As a result, the application developers don't have to worry about writing those low-level steps. To make the discussion of inversion of control more concrete, let's take a look at the acceptor connector and reactor frameworks, which we'll be covering in great detail in later parts of the course. If you recall from some of our earlier discussions, the reactor essentially is used to run the event loop for an application, for an event-driven application. And when you call the reactor's event loop, it goes ahead and uses the underlying synchronous event demultiplexer, such as select or poll or dev poll, or wait for multiple objects if you're a Windows user. And when events occur, the reactor will demultiplex the events to the appropriate event handlers and dispatch callback hook methods to do the actual work. You can take a look at an article I wrote on the reactor framework many years ago at this URL. Here's another view showing some of the other interactions, the more dynamic interactions between the various roles and responsibilities in these frameworks. You typically register a number of concrete event handlers, things like acceptors or service handlers that carry out various operations. And the reactor stores pointers to those handlers along with handles that correspond to the sources of underlying events. At some point, the application turns the control flow over to the reactor framework, and from that point onwards, the bulk of the processing is driven by inversion of control. When interesting things happen, the reactor calls back on the event handlers to do their thing. There's another paper you can take a look at that gives other dimensions of the reactor framework. In addition to inversion of control, frameworks also provide integrated domain-specific structures and functionality. Here are some examples of various types of domains you might find frameworks embodying. Some of these domains are what we might think of as application domains, things like electronic stock trading, various types of social media, perhaps mobile applications running on your smartphones. Other domains are more infrastructure domains, things like networking, concurrency, graphical user interfaces, database access, and so on and so forth. They're both important sets of domains, and in the course, we'll primarily be focusing on the infrastructure domains for concurrency and networking. But of course, the purpose of these domains is to support the applications that are written on top of them, for the most part. Here's another dimension of how frameworks support domain-specific structures and functionality. And they do it through a combination of different features. Typically, frameworks provide abstract and concrete classes, as well as canonicalized flow of control through those classes. Here's an example, once again, from the Acceptor, Connector, and Reactor frameworks. Typically, the way you use this, for these frameworks, is you initialize some endpoints in what's called passive mode. In other words, they're waiting for connections to come in. And then there's a template method, which is part of the Acceptor Connector framework. And when a connection arrives, the Reactor dispatches this template method, and it turns around and performs canonical control flow interacting with the various structures we just talked about. So it will go ahead and accept the connection. It will create some kind of service handler to handle the connection. And then it activates the service handler. And at this point onwards, if we're implementing a purely reactive solution, then the application-specific or service-specific processing that's done by the service handler will be driven by callbacks from a reactor as well. These steps, these various parts of the flow of control, are very common in the domain of networked applications and network services. And you can take a look at a paper at the URL below that gives more examples of how acceptors and connectors work together with the reactors to provide integrated domain-specific structures and functionality for the networking domain. One of the other characteristics of frameworks that's important is that they are essentially semi-complete applications. And what that means is that the application is largely inherited or composed of reusable artifacts coming from the framework, and at certain selected points, sometimes called hotspots, these are points of variability, applications can define their specific processing logic, which are invoked by the framework through so-called hook methods, which are typically either functors or virtual functions that are dynamically bound in order to be able to call out to application-specific code to do the kinds of things the framework just doesn't know enough about because it's really part of the application responsibility. So how do you complete a semi-complete application framework? Well, this typically involves instantiating objects and subclassing and overriding various hook methods in order to be able to move from the semi-complete application, such as the Reactor and Acceptor Connector frameworks, to then go ahead and add in the additional capabilities that are specific to a particular application or some type of higher level service. Once again, there's a paper you can take a look at that will give you more examples of applying these frameworks and others in the context of communication gateways for telecom systems. So to summarize this part, the quality of software and the productivity of software developers has historically lagged behind the quality of hardware and the productivity of hardware developers. There's lots of reasons for this. A lot of it has to do with inherent complexities of software and the kinds of things we expect software developers to do, which are often much more open-ended and complex than the kinds of things that hardware and hardware developers are expected to do. There's also accidental complexities. These are things we bring on ourselves by the fact that we historically, as software developers, have had a tendency to use low-level languages, low-level operating systems, low-level tools, and we've also had a tendency historically to use design techniques such as top-down, stepwise refinement and algorithmic or function-oriented design, which makes our solutions overly brittle and hard to extend. These kinds of problems are particularly challenging for concurrent and network software, where performance and quality of service have often been of paramount concern. It's also the case that people historically have had a tendency to rediscover and reinvent many core components, abstractions, structures, functionality, and so on throughout the software industry. And even though this is often a lot of fun from a developer point of view, it's also prohibitively expensive because you have to spend way too much time building the software and trying to debug it and test it to get all the defects out. Frameworks can help improve quality of software and productivity of software developers in a couple of ways. Most importantly, they embody these common design and implementation techniques, these patterns, these recurring approaches, so that application developers don't have to learn them and implement them on their own. Instead, they can leverage the proven techniques that have been applied successfully by others, doing similar but not necessarily identical kinds of things. And the other way in which frameworks help to improve software quality and productivity is by amortizing the quality assurance effort and the various artifacts that are produced to help with quality assurance, such as regression testing, such as test-driven development, such as continuous integration testing. These techniques are very valuable and can help to automate many steps which historically were done in a very tedious and error-prone manual way. If you take a look at this URL, you'll find more information about some of the open source quality assurance environments we've developed to make it easier to build and debug and validate the software we produced over many years. As a parting thought in this part, we still have a long way to go to match the way in which hardware engineers are able to leverage higher level modeling tools and modeling approaches, things like CAD tools for doing chip design and synthesis of complex systems. It's beyond the scope of this particular course to go into this in detail, but there's been a lot of progress over the past decade at helping to raise the level of abstraction used to develop software, especially software in certain important mission-critical domains, things like embedded systems or various types of enterprise systems, where we can apply domain-specific modeling tools and model-driven engineering. And I encourage you to take a look at the link here for one example of such a tool that we've developed that can be applied in an open source way for some aspects of improving the modeling of software.